In this video, the third in my series on mastering vectors, we're going to look at everybody's favourite question, forces on a slope. Yay, more vector components. There's the slope, and I'm going to put the cycle as just a box. It's too hard to draw any other way. What forces are acting on the bike? Let's just pretend for the moment that the bike is in equilibrium. It's got no resultant force acting on it. It's in equilibrium. So what forces are acting? Well, there's two that we have to think about. The first one is the easy one, and that's the weight. The second one is what's known as it has lots of names. It's called the contact force, the reaction force, the normal reaction force. I like to call it normal reaction force because it's telling you the word normal in maths means 90 degrees. Okay, and that's the only forces that are acting because we're going to, ignore friction as we always do. Now, here's an interesting thing here. All the way through this work, what we've done is we've taken a vector and we split it into x and y components. Now, what we're doing there is assuming that we're thinking about a piece of graph paper with x and y going across the page, kind of like that. Is there any reason why we can't put those axes like this? So what I'm going to do is take my x and y and line up x so that it goes along the slope. All the trig rules apply exactly as before, but what this means is that our reaction force is exactly along the y-axis. That definitely makes life a lot easier. So what we're going to do now is take W. We can think of our journey from this point to that point. We can think of it as going this way and then that way. Now, the first of these is moving directly along the y-axis, but in the opposite direction. So we could call that for the moment WY, but be dead careful here because it's not the usual y-axis that you're used to thinking about because we've kind of rotated it a bit, haven't we? Either way, it's 90 degrees to the slope, which means it makes no kind of difference to why it's harder to ride up and down the hill. What we're interested in is this second one here, which I suppose we could call WX. Now, WX is the component of weight acting down the slope. If you stop pedaling up the hill, then you stop providing an upwards force, which means that you will have a resultant force down the hill of what we've called WX, the component of weight down the hill. Therefore, in order for you to stay balanced, you have to provide some sort of driving force or a braking force or something up the hill that's equal to WX, and then you'll stay still. Where's 30 degrees? So 30 degrees is here. Now, when I was at school, I had to just learn this because I didn't get it. But this angle here, by similar triangles, which I'll leave you to think about, if that's 30, then that one's 32. It's because you have a bisector across the slope, which is at 90 degrees. Therefore, that's going to be 30. So we know that's 30 degrees. So why is it harder when you're going at 60 degrees to go up the hill than it is at 30? And you would say, because it's steeper. And that will get you no marks at all, because what they want you to say is, coming back to this, WX actually equal to your weight times sine 30 degrees. Hopefully you remember that sine 60 is bigger than sine 30, therefore WX is a bigger force down the slope at 60 degrees than at 30, and so at 60 the steeper hill is harder to climb. So actually the whole slope thing, it really becomes clear when you get your head around where this angle 30 is and about moving the x and y axis kind of like this, like we said at the start. If you found that video on slopes for A-level physics questions useful, then check out this next one, which attempts to answer why it is that forces at 90 degrees have no effect on each other.